Welcome to the world of the magic triangle. More formally known as Pascal's triangle, this simple geometric arrangement of numbers is one of the most powerful tools in mathematics. From probability to algebra and even the patterns of nature, it holds secrets that have fascinated thinkers for over 1,000 years. Today, we unlock them all. At first glance, it looks like a simple grid of numbers, but from this simplicity, an entire universe of mathematical complexity emerges. While named after Blaise Pascal, he wasn't its only architect. The history of this triangle spans centuries and continents. In India, the mathematician Pingala explored these patterns as early as the 10th century, using them to describe poetic meters. In China, Yang Hui was writing about the triangle in the 13th century, long before it reached the Western world. It wasn't until 1653 that the French polymath Blaise Pascal organized these properties into a formal treatise, applying them to gambling and probability. So, how do you build this mountain of numbers? It starts with a single 1 at the very peak, which we call row 0. The first rule is simple. Every row starts and ends with a 1. These form the edges that hold the triangle together. To find the interior numbers, you look at the neighbors above. Each number is the sum of the two numbers directly above it. For row 3, we add 1 and 2 to get 3, and 2 and 1 to get 3 again. The pattern repeats row by row. This pattern continues indefinitely. No matter how deep you go, the rules remain the same, creating an infinite mountain of data. Inside this grid, we find incredible order. Let's look at some of its key characteristics. First is symmetry. The triangle is a perfect mirror image of itself. The left side is always identical to the right. First is symmetry. The triangle is a perfect mirror image of itself. The left side is always identical to the right. Next, look at the horizontal sums. If you add up every number in a single row, something amazing happens. Row 0 equals 1, row 1 equals 2, row 2 equals 4. Each row sum is exactly 2 to the power of that row number. The total capacity of the triangle doubles with every single step down the mountain. This is fundamental to binary logic and information theory. Now let's look at the diagonals. Each one contains its own special family of numbers. The first diagonal is all ones. The second diagonal contains the counting numbers, the very basics of arithmetic. The third diagonal gives us the triangular numbers. These represent the number of dots needed to form an equilateral triangle. But these are just the basics. If we look closer, we find hidden masterpieces of geometry and nature. What happens if we color only the odd numbers and leave the even ones white? We reveal the Sierpinski triangle, a famous fractal. This shows a deep connection between discrete numbers and self-similar geometry. Even more surprising is the connection to the Fibonacci sequence found by summing along shallow diagonals. By adding these diagonal paths, the triangle miraculously generates the sequence that defines flower petals and spiral galaxies. The triangle even has tricks for quick summation, like the hockey stick pattern. Start at any one on the edge and move diagonally. The sum will always be the number just below the end of your diagonal in the opposite direction. In the world of algebra, the triangle is an indispensable shortcut for expansion and combinations. When we expand a binomial expression like a plus b squared, the coefficients 1, 2, and 1 come directly from the second row. This works for any power. Row 4 gives us the coefficients for a plus b to the fourth power. It's an incredible time saver for polynomials. This also makes the triangle the ultimate tool for combinatorics, the math of choosing. If you have 5 objects and want to choose 2, you simply look at the 5th row and the second entry. The answer is 10. Every single entry in the triangle represents a unique combination, saving us from complex factorial formulas. Because of these combinations, the triangle is also a map of probability in the real world. Take flipping 4 coins. The outcomes, all heads, mostly heads, or a mix, perfectly follow the ratios in row 4, 1, 4, 6, 4, and 1. It predicts the distribution of chance, showing us that even in randomness, there is a predictable mathematical structure. From its ancient roots to its place in modern information theory, Pascal's triangle remains one of the most elegant structures in math. It is a bridge between simplicity and complexity, showing us that the most profound patterns can grow from just a few simple rules. Thanks for watching.